So the title of this unit is called Equilibrium. If you are in equilibrium, what that really means is two ideas. It means that the net force on you is zero, and the net torque on you is zero. Now, I haven't explained yet what torque is. That's next lesson. What it really means, Sam, is this. You're not moving and you're not spinning. Because you could be spinning in one place and you could argue you're not moving. That means there's an unbalanced torque on you. Or you could not be spinning, but you could be accelerating. Okay, that means there's an unbalanced force on you. And today's lesson is going to be a nice review of some of our key force concepts, which is good. Today we're going to be looking at what's called translational equilibrium. What do you need to guarantee that you're standing still? Or if you know you're standing still, what do we know? For a body to be, I wrote, in translational equilibrium, the following condition must be true. What the heck does that mean? What does that funky M on its side mean? The sum of all of the forces is zero. That's one approach that I use. Another way of writing this is to say the sum of all the horizontal forces has to be zero, and the sum of all of the vertical forces has to be zero. If you're standing still, I know that. Or if I really, really want to break it down, especially if the picture is nice, all of the forces to the left equal all of the forces to the right, and all of the forces up equal, take a guess, all the forces down. I use that last one if I notice in the picture that all of the forces that I'm dealing with are up, down, left, right. If they're slanty, I use the very first one. I say the sum of all the forces is zero. Like example 1. So here is the physics of hanging a sign. We have a mass, 12.6 kilograms. It's hanging from 2 ropes, and the angle that they form in each angle is 34 degrees. So it's hanging nicely in the middle. Focus here. It says find the tension on each rope. I could, Nathaniel, if I wanted to, break this up into its horizontal and vertical components, break this up into its horizontal and vertical components, and then I could say all of the left forces equal all of the right forces, and all of the up forces equal all the down forces. Instead, I'm going to say I know that the sum of all the forces is zero. Have I said the word force several times? I have. How do you think I'm going to start this question? How did we begin the vast majority of our force questions? What was the first thing that we did? This is a good review, by the way. No, before we wrote anything like F equals M, F equals win or minus, before we did that. A free body diagram. You know what? Now, we're not going to draw a free body diagram on the mass. We're going to draw a free body diagram where the ropes join. So let's put a dot right there. What are the forces acting at that location? Get the obvious one. Hey, this sounds familiar. Sorry? mg. And then it looks like I have a tension going this way. I'll call it tension L. What does L stand for? Left, cleverly. And I have a tension going this way. I'll call it tension R. What does R stand for, cleverly? Right. Those are the only 3 forces acting at that location. And I know what they add to. 0. Now, how am I going to show that? I'm going to do this vectorially. I'm going to add these 3 vectors, tip to tail, tip to tail, tip to tail, to get a triangle. Oh, and what will 0 look like in the triangle when I add these 3 together? I'll end up right back where? Where I started from. That's going to be the definition vectorially of 0. So we're going to draw this. This is your first introduction to adding 3 vectors, and here is my strategy. When you're adding 3 vectors, always draw the easiest vector first, always. What's the easiest vector here? I'm going to draw that first. Then I draw the toughest vector second. These are both equally tough. So I'm going to go off to the right. But now that I've done that, I know where left has to end up, because what did you tell me that the net force adds to? Which means in my vector diagram, I better end up where? Okay. I need some angles. Well, it said that this angle here was 34 degrees. Why don't you write that in the diagram? But then don't write this next bit down. I'm going to muck up this diagram, but I don't want you to muck yours up. Do you notice that theta is by a horizontal line and tension left? If I add a horizontal line, don't write that. How big is that angle then? 34 degrees. How big is this angle? Because what do those two add to? So this is the angle we're going to fill in. How big is that angle? 56? Write that down, please. You're going to find in many of these triangles, it helps really lightly to add a dotted horizontal or vertical line. Horizontal if they give you a ceiling in the picture. Vertical if they give you a wall in the picture. Because that's going to be your frame of reference. Oh, and how big was this angle up here? 34. Now that goes with tension right, so I know that that's 34. Folks, how big is that angle right there? Focus here, please. How big is that angle right there? 34. So don't write this down. How big is this angle? How big is a horizontal line pointing upwards at tension right? A horizontal line pointing, how big is this angle? 34. How big is this angle? Shashan, welcome here. Glad you made it. Better never late, though. Get one of each of those, please. Oh, if I know two angles, I always know the third one, because what does every triangle add to? So what's the third angle? 68. Okay. And not only that, I know one of these sides. Which one of these sides do I actually know? MG. That's going to be my attack point. By the way, is this a right angle triangle? Can I use SOHCAHTOA? This is going to be a sine law or the cosine law. Look. You said I know that? I know that. I have a pair. Oh, way back from lesson 1 at the beginning of the year, this is a job for which one? This is the sine law, which I think is way faster than trying to break this now up all into vertical and horizontal components. You could break this guy up into tension left up and tension left that way. You could break this guy up into tension right up and tension right that way. You could cancel all your ups and downs with all your... I can do this in a few lines. I can say, you know what? Since I'm going to find tension left and tension right. What do you want to find first, Dylan? Left or right? I don't care which.
Left.
Left. So I'm going to start out with my plan of attack with the pair that I know. Sine 68 over mg equals, and it's going to be those two. Sine 56 over tension left, right? That's how the sine law works. Are you saying now this is just cross multiply? Similar to the transformers that we did last day? Wow, straight cross multiply. In fact, I think it's going to be tension left is going to be mg sine 56 divided by sine 68, which is what? M was 12.6. Sorry? What do you get? Sorry, equals what? 110? Pardon me? Because the two original angles are the same, because we hung the sign dead center, I think tension right is going to be the same. Let's just convince ourselves. I'm going to write the equation for tension right, and it turns out when I write the equation for tension right, I get sine 68 over mg equals, you said I wanted to find tension right, and because its opposite angle is also sine 56, yeah, tension right is going to be also 110 newtons. You'll notice I didn't bother asking you for a direction. Why? Because the angles are contained in the triangle there. What if we didn't hang that sign dead center? What if we slid it along the ropes a little bit off center? Kind of like this. Well, now I don't think the tensions are the same. It says find the tension on each rope of mass 1, still 12.6 kilograms. Theta is 44 degrees and alpha is 16 degrees. You know how I'm going to start this? You know what I'm going to do first? Darn right, I'm going to do a free body diagram. Get the obvious one. And then it looks like tension left is a little steeper. I'll exaggerate it a bit. And tension right is way shallower and longer. I'll exaggerate that a little bit. Put the phone away and move in, kiddo. And power it off, because yours was the one that was vibrating, right?
No, it wasn't.
Wasn't you? Okay. Which one am I going to do first? Always the easiest one. Which is the easiest force? Okay. Then I do the toughest one next. They're both kind of tough, so I'm going to go to the right and then come back to the left. Kind of to the right is going to be shallower. Like that. To the left is going to be steeper. Like that. I find the trickiest part is getting the angles. They gave me a horizontal ceiling. I'm going to use horizontal lines as my reference. Cole, my friend, how big is theta?
44 degrees.
So if I add a little horizontal line right there, how big is that?
44.
I want that. 90 minus 44, which you may be able to do in your head. Okay, that's 46 degrees. I can erase my lines. You folks can do it really lightly in pencil or a dotted line in pen, whatever you need to do so that you know what the heck we did. Joe, my friend, how big is this angle?
16.
And how big is that angle? Also 16. That's the alternate interior Z rule. So how big is that angle? By the way, you notice what I'm trying to do is set up a horizontal line going up to the tension. Horizontal line going up to the tension. 16. How big is the angle that I want? 74. And now I can go third angle in a triangle. Oh, that's 110, so 120, 60. Is it 60 even?
Yeah.
It's kind of nice numbers. Which one do I know? MG. By the way, could I also, Chase, give you the tension in one of the ropes and say, can you find the mass that we can support? Sure. Or find the tension in the other rope? Sure. All you need one of those three, all three angles, and now it's straight sine law, cross multiply. So I'm going to divide this into two. I'll find tension left, then I'll find tension right. Finding tension left is going to be sine of 60 over mg equals, which angle goes with tension left, the 46 or the 74? You're right. Say it. What? Someone was right. It's 74, right? Always go across. Sine 74 over tension left. I think tension left is going to be mg sine 74 over sine 60. M G sine 74 over sine 60. And I get 137 newtons. Double check, did I type that in right? Looks good. 137 newtons. To find tension right, I'm going to use, again, the sine 60 over mg But this time for tension right, which angle goes with tension right? The 46 degrees. Cross multiply. In fact, I noticed this is almost exactly the same equation for left, except instead of a 74, I have a 46. You know what? I've got a good calculator. I think I can just backspace and change the 74 to a 46. 103. So what I've been using here, Kevin, because all the forces are at yucky angles, and I know it's in equilibrium, it's not accelerating, I've been using the sum of all forces is 0, but I've been doing it, Nathaniel, vectorially. I've been saying that means as a triangle, you're going to end up back where you started from. The second approach that I sometimes use is that everything left equals everything right, everything up equals everything down. I use that if all of the forces in the diagram are all vertical or horizontal or both, but nothing is at angles, kind of like the next one, the bridge. I noticed looking at this diagram, every force is in the vertical direction, in the y direction. So rather than going all triggy, I'm going to say, you know what? Everything up equals everything down. What are my forces up? 1900 and? What are my forces down? Mr. Dueck? Yes, Sebastian. Why does the bus weigh like 77 kilograms? Shut up, I was just making up numbers. Because if you divide that by 9.8, it's a really light bus and bridge. It's toys. It's a toy bridge. It gets the point across. So here's some of the physics involved in bridge building. What do you get? It's going to be just minus 1900. Yeah, just minus 1900, right? 5800 plus 760 minus 1900. 4000. What do you get? Sorry? 4660? Is each post exerting the same force up? Is FA and FB the same? Why not? The bus is closer to one of the posts. In fact, as this bus slowly moves to the left, what's going to happen to this force? Gets bigger. What's going to happen to this force? Okay. What we're going to ask ourselves tomorrow is, what if you don't know either force? What if you're missing both of them, so you have two unknowns? Now what? This is the physics of bridge building. And we're going to introduce the idea of torque, of rotational equilibrium. And torque is nice because even if you have two forces that you don't know, by being only a little bit clever, you can eliminate one of them and find the other one. Oh, and then once you found the other one, then you say everything up equals everything down. Turn the page. Example 4. What is the minimum coefficient of friction? Oh, hey, this is great review of forces. I guess they want me to find mu required for the 12.3 kilogram mass to hold this system in equilibrium. Okay. How am I going to start? What am I going to do first before I do anything else? Yeah, and you know, but instead of doing a separate free body diagram, since I have more than one mass, this is kind of actually like an Atwood machine without the pulley. I'll label the forces right on my picture because I think that's going to be a little clearer. So let's start with the 5.25. What are the forces acting on it? Get the obvious one. More than one mass? Is there more than one mass in this question? I'll call it M1G, right? Remember?
Yeah.
This is good review of all of our approach for forces, which is kind of nice to end with this. What else? Well, it looks like I have a tension left, and it looks like I have a tension right. By the way, see the lovely 90-degree angle? I'll bet you this triangle I won't need sine law or cosine. I bet you I'll be able to use SOHCAHTOA. I bet you, but we'll find out. Let's go walking to the 12.3. What are the forces acting on it? Get the obvious one. M2G. What else? Normal force. It's on a surface. What else? Okay. Friction which way, first of all? To the? Now, the tension is pointing to the left, but since forces come in pairs, Brett, I'm pretty sure actually in terms of magnitude, that's the same as tension R, is it not? Okay? All right. Is that okay? Right? Forces come in pairs. Okay, because that was, remember the tensions always can't, I did my, get rid of tension, dumb joke or whatever. What are we being asked to find? All right, let's see if we can write an equation then for that right-hand mass, which has friction as part of it somehow. Who's winning? It's a trick question. Nothing. It's a tie. In fact, in that right-hand mass, I think what we're saying is friction equals tension right. It's a tie. Friction is what times what? U times the normal force? I don't know the normal force. Oh, but look. I know another force the same size as a normal force. What? Good review as well. So I'm going to have mu m2g equals tension right. I want to find mu. Do I know m2? Yeah. Do I know g? Oh, this is easy. Do I know tension right? Not yet. Oh. Suggestions? How? Let's go look at mass 1. Okay? Let's add those three forces together vectorially. And I know I'm going to end up back where I started from because I know that the force is 0 because it says it's in equilibrium. So I'm going to draw this as a vector triangle. Draw the easiest force first. What's the easiest force? M1G. Yoink. Draw the ugliest or toughest force next. What's the toughest force? Yeah, and here's why. Because what does the third force look like? It's exactly horizontal. I know what it's supposed to look like. So tell me when to stop. 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 Right there. Sometimes I make mistakes. Okay. So if you're drawing a vector diagram, easiest first, ugliest next, second easiest last. Oh, and we have mg tension left, and what I'm trying to find, tension right. See the angle that they gave me? 42. Next to what? A vertical or a horizontal wall? So I notice this. Next to tension left and a vertical is 42. Here's tension left. If I add a vertical, what's that angle? What's that angle? It's also 42. By the way, you could use the 48 up here as well. I always like to try and see if I can actually use the number that they gave me in the diagram in my actual diagram, just because I'm a nerd. Oh, and this is a lovely right angle. So tension right, opposite adjacent or hypotenuse. I can use SOHCAHTOA. Tension right, opposite adjacent or hypotenuse. Really? Opposite adjacent or hypotenuse, boys and girls. What about mg? Adjacent. Which trig function? Tan. Tan of 42 equals what over what? Tension right over mg. Can you get tension right by itself, please? Oh, which m? You know what? M1g. I got two masses. Graydon, you pointed that out, so I should be careful. Yes? How would I get tension right by itself? Okay, so an expression for tension right is M1g tan 42. So what you're saying is, I could replace that over there. I'm going to write down below. By the way, you can see that normally I get to this unit right around Christmas time. So here is the Christmas card for smart people. We have the letter M. Calculus students, what is 2.71828? It's used as part of ln, but what constant? Okay, that's the number e. Another way to write r squared would be rr, yes? And what is 1 over y to the negative 1? What's the reciprocal of 1 over y? Just plain old y. What's the square root of x squared? X. And what is force divided by acceleration? So there is your Christmas card for smart people, H2O, H2O, H2O. Meanwhile, let's keep going here. So you're saying that mu equals m2g, sorry, mu m2g, no equal sign, Mr. Dueck, equals m1g tan 42. Oh, cool. What do you notice? Sorry? Gravity cancels. You know what that means? This setup would work without any adjustment on the moon. It would still be in equilibrium. Or on Mars, it would still be in equilibrium. Or on the sun, if you could somehow do it, it would still be in equilibrium. What are we trying to find? Let's get the mu by itself. Mu equals m1 tan 42 divided by m2. What was m1, Mr. Dueck? 5.25. Tan 42 divided by, what was m2, Mr. Dueck? 12.3. .25 tan 42 divided by 12.3. 0.38 units. Oh yeah, mu is just a ratio. It's a unitless measurement. Nice, some nice review of forces there. Good for our year end as well. Turn the page. Or next page over. Example 5, in the diagram below, assume the mountain climber's feet are tending to slip down, so friction is up, the climber is at rest. This is actually a really nice little application question, but in the interest of time, I'm actually going to temporarily nuke it, and I'm going to say we're going to jump to example 6. We're going to finish off with example 6. Friction does. The coefficient of friction does not, because it's actually a force divided by a force. It's newtons divided by newtons, which would cancel. Right? If you get the mu equals, friction equals mu times the normal force, divide by normal force to get mu by itself. You have force over force. Yeah. Hey, number 6, try this one on your own. That's 21. That's 40. 19. Dueck, that's not 19, that's mg. Don't just put the mass on there, meathead. get a decimal. mg sine divided by sine. Let's see if you get what I got. Yep. So this is the physics of hanging signs. Question for you. So here's the question. It says this. Specifically, I want to talk about 5B. Here's a traffic light. And 5B says, explain why it's not possible to get this cord absolutely straight between the two supports in this static equilibrium situation. Explain why you can't get that 90 degrees and you can't get that 90 degrees. Sorry? Yeah, there's no vertical force component up. There's no possible way it can be in equilibrium. That goes back to that third definition where I said, well, you can just think about it as everything up equals everything down. If you've got down and no up, in fact, a little demonstration for you. What's your homework? From the great big unit review that I gave you, you can do, I think I assigned 5 questions. So you can do number 2. Number 2, they're giving you both tensions, and instead they're saying find the weight, or mg. Number 6, you can do number 6. Write down these questions, please.
All our homework from this.
Yep. Number 10. Number 10 is very similar to the one that we did earlier, but instead of asking you to find the coefficient of friction, they're giving you the coefficient of friction, and they're saying, hey, how big does this mass have to be? Little twist. And I skipped a few. 15 and 22. I'll throw an online answer key showing all my steps if you guys get stuck tonight. Okay? Don't hand this in Monday. I'm going to be assigning more questions from here. This will be like a 40-mark unit assignment that you'll hand in at the end of the unit after 2 more lessons. Some cool videos to show you.